hands. How many of you chose the left side to be the given? How many of you guys chose the right side to be the given? Split both ways. That's all right. I'll show you both. Oh, I don't want that though. Hold on. Let's do single page. And let me add a page. And then do dual page. Got it. I'm going to go ahead and copy and paste this real quick just so I can go ahead and let's do clone. That's easier. All right. Now you might not have known the snazzy way of doing it with T, hence why it's called a T proof, not just trigonometric proof, but T proof. The T helps you keep everything honest in the sense of once you've chosen a given, showing me and being like, I chose this as my given. Why? Because you're starting here. This is a way of showing me what you chose to start as your given. The rest of you guys, when you, or as you now from here on out, do these verifying problems, you're going to draw a T. Literally, I give you like half a point just for drawing the T. And picking a side and being like, look, it's my given. Some of you chose that as your given. Some of you chose that as your given. Whatever you chose, you had to go from the given to the proof. So over here, there were a couple different ways to go. I think what I would have done, as far as how to proceed, would have been changing this guy to cosine squared t over sine squared t, and changing cosecant to 1 over sine. I think that's what I would have done. Why? Because I see lots of sines over here. And so I'm like, maybe I should change everything to sines and cosines, and maybe the cosine will just kind of work out. Over here, I think I would have been like, well, it's a Pythagorean. So maybe I can change 1 minus sine squared to cosine squared. Over here, I would have been like, uh-oh, I have a complex fraction. We have two different options. One is to rewrite this divided by that and then change it to multiplication of the reciprocal. The other way is my nifty, nifty trick of multiplying top and bottom by that nasty little denominator who's kind of messing everybody up. When you multiply by the reciprocal, that goes away and I didn't have to rewrite it. I'm just lazy. But then what happens? Wait, don't those reduce? This is sine times sine. And so what's left? And some of you might have gotten a little confused here. But remember, sine squared is sine of t squared, aka sine of t sine of t. So one goes away and one's left. Ah! Wait, you have to keep going. You have to get all the way from the given to the proof or all the way from the given to the proof. So over here I might go ahead and, oh dear. Well, I guess I could look over here and see that this guy should have a cosine squared over sine squared and be like, I only have one. Well, maybe I can, and this is a very creative step that is a very hard step to do, maybe I can multiply top and bottom by the over sine squared that I want. But what I do on top, I have to also do on bottom. Ooh, maybe that's hard. Maybe this one was a better given to start with. Over here, I can now go ahead and say, hey, isn't cosine squared 1 minus sine squared? Ha 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 ha. Now, how do you show me that you realize you've gotten to the end? Check mark, but technically first you say, hey, look, he matches. And as you're writing it, you're making sure that everything checks out, and you're like, it's exactly the same. Done. Here's the given. You've gotten to the proof, and you're like, look, it's my proof. Dun, 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 dun. Over here, this huge creative, what? You brought this out of nowhere. Well, no, I knew cotangent squared. I looked over there, and I was like, isn't that cosine squared over sine squared? I need an over sine squared, but what I do on top, I have to do on bottom. And now I'll end up with, hey, look, that's cotangent squared. And hey, look, sine over sine squared, that's 1 over sine. Now I've made it match. Was it possible from both directions? Yes. But which one would you guys say was the trickier way to go? This, because this looks like magic. It's not. It's math. Creative math is sometimes hard to come up with on your own. So pause. Was anybody wrong for trying this side? No, there was a way. But just because you start one direction, does that mean you have to finish in that direction? No. Sometimes in section 5.2, it might be good to be like, this isn't headed in the right direction. I don't know what's going on. I'm going to put a line through this, and I'm going to try it this way. Maybe it's easier, and maybe it is. And maybe it's not easier. Isn't this one technically kind of shorter? Maybe some people will be like, that's not easier, that's longer. But it was easier on your brain. It's going to be different for you guys. Now, sometimes the easy way is the easy way, and it's going to be the easier way for everybody. And this problem, I think, probably for most of you, if not all of you, this is the easier way. To be honest, for me, this is the easier way. But maybe for some people that are a little bit higher or faster or do a lot of mental math with trig, this would have been the easier way. I don't know. But in this section 5.2, I need you guys to try to suspend judgment, both of yourselves and of others, as far as how you attack problems. Does that make sense? Someone's going to choose the left, someone's going to choose the right. Are you going to judge them for that? No, just be like, actually, I think my way is easier. Okay, cool. Let's show them that, because maybe that'll help their test problem later go faster. Is it something to be like, ugh, I can't believe you? No, it doesn't matter. What we're trying to figure out is, are you doing legal steps and are you learning along the way? Now, guys, have we even done section 5.2? Hey, look. So why did I give you this? To remind you, as we grade section 5.1, why we did it. What was section 5.1's title? All it was trying to train you at how you can use them. How you can use identities to help you change stuff up. And there were little hints along the way with factoring and simplifying and common denominators and substituting and other types of specific directions that were like, hint, 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 by the way, you can. Because when you get to section 5.2, what are the directions? Verify. Do what you need to do to legally show me that given is that proof or this given is that proof. They're not going to give you hints. And guess what? CalcChat doesn't always do it in a nice way that makes sense or in a way that your brain would think of. So just using CalcChat and being like, oh, I don't know how to do it, I'll use their way. Is that way going to make sense in your brain when you have to do it on your own in the test? Maybe, maybe not. Does that make sense? Okay. And one more thing. In CalcChat, they don't make the T's. They don't organize their information. They don't clearly show, here's my given, here's my proof, it matches, haha, done. But guess what I want you to do? Draw the T. Here's my given, here's my proof, ha, it matches, done. And if you mess up that format, I take off points. Wait, so when I check your Google Classroom homework and I see it looking exactly like CalcChat, I'm not going to be happy and give you a 0? Mm-hmm. But no one started 5.2, hopefully, yet. We haven't even started the section. If you have, a little bit overachiever, tone it down a little bit, but coming back. I don't want your homework looking like CalcChat on this one. What do I want? T's. What do I want? Choose a given. Choose a side. What do I want? See if you can get to the proof. If you do, have a little party and be like, it's my proof, done. And then I can give you all the points. Sound good? Robbie. Let's grade. Color pens at the ready. Section 5.1. Let's see how well you figured out how to use your identity. What? 1 through 6 was just fill in the identity? Go team. Go team. Hopefully that was easy. Hopefully you just pulled it straight out of the formulas. Why was number 6 a negative? Was it the odd property? Yeah. Yeah. Okay, now let's have fun. Number 16 was B. Number 22, some of you might have tried to go farther, and there's no judgment for trying. Some of you might have done tangent squared is sine squared over cosine squared. Sine squared times sine squared is sine to the 4th over cosine squared. You're right. It just didn't really get any simpler past this. Nothing reduced, nothing went away, nothing can change to be anything easier. So you could have kept going. If you have sine to the 4th over cosine squared, I say great job. But circle this guy as like, well, it didn't really get any better. And how is that practical for section 5.2? Are there steps you guys can take that will change whatever is there to look like something different? Yes, but sometimes you're going to start making it worse and worse and farther from where you want to go. Does that make sense? Okay. Number 32. Factor. Class 1. Why? What did you want him to be? A cosine squared. Wait. He can be. Is that mine? I am so sorry. Traffic slowed me down. I just went rushing into class today. Sine squared can be cosine. Well, it can't be cosine squared, but it can be 1 minus cosine squared. So the very thing that you guys got frustrated at, the very thing you were like, I wish it was a cosine squared and it's not. Wait, but there's a property. Now, did you have to do some like combining like terms to make it into something you can factor? Yeah. 1 plus 3 is 4. Okay. Ew. Who's in front? Pull them out. Okay. Now factor. Oh, don't you have minus 4 and plus 1? Dun, 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 dun. Don't forget the negative in front. Some of you might have the negative distributed in. Now careful, it wouldn't go everywhere. If it goes everywhere, you're messing up and killing a poor little seal. But he could have been like a negative cosine minus 1 or a negative cosine plus 4. But yeah, you're right. It was frustrating. It wasn't a cosine squared, but you had an identity. You were supposed to learn how to use an identity to make it possible. Using identity is the title of the section. Ooh, hoo, 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 hoo. Ah! What did Calc Chat jump over and be like, psh, that was easy. You guys didn't even need me to show it. What on earth happened from here to here? To go from 2 separate fractions to 1, what's that process called? Common denominators. So real quick, just in case someone might have made a mistake in the common denominators, to get from there to there. To be honest, I totally relate with the Calc Chat dudes. I could have done that in my head too, but for a lot of you guys, that's a little too rough to make that jump. And if I check your Google Classroom homework and I'm like, they made that jump, wonder if they went to Slater for that one. Although Slater's, usually they show a little bit more work. What's the in-between step to get from here to here? Yeah, multiplying by cosine over cosine, because that's who that guy's missing. Multiplying by 1 plus sine over 1 plus sine, because that's who that guy is missing. You end up with cosine times cosine is cosine squared. One plus sine. Oh, I guess I could write that as 1 plus sine x squared. I guess I could do that and just say it's squared, which is what they ended up doing, because look, all they did is take these two and put them. But eventually, aren't you going to have to rewrite this guy? So maybe you can even do it better than they did and be like, wait a minute, I have it all nice and written out. Isn't that 1 plus 2 sine of x plus sine squared of x? I would have actually done that. I would have done better than they did. But it's up to you. You could have written it, I guess, as 1 plus sine of x squared. I think this is going to be more helpful to what I'm supposed to do soon. And I would have gone from there instead of doing some, hey, look, trick. But then where'd you go from there? What's cosine squared plus sine squared? Addition is commutative. You can put this in any order you want. Squared of x plus sine squared of x. 1. What's 1 plus 1? 2. Oh, there's a 2 in both. Ooh, ooh, ooh. Dun, 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 dun. Mm-hmm.
I'm guessing that you'd be killing something. Maybe,
If what?
if you tried to have the 1 plus sine x, 1 plus sine x.
Yeah. The reason is the addition. Remember, the same way I have to distribute with multiplication across addition, I have to distribute division across. Division is really multiplication of a reciprocal. So division is multiplication by 1 over. So the same way that multiplication has to behave, division has to behave. So if you cancel, you're like, oh, you don't need him. Yes, he does. Yes, he does. Make sense? Now, Kyle, if there was a 1 plus sign in both, then I could pull it out. Then I could legally. But he doesn't have one, so I can't take him away. Number 54 was a substitute. And it was a lot like the one we did in class. P.S. There's one of these on the test. What? You might want a special highlighter that you have just in case I give you hints. Anyway, plug and chug. 7 sine becomes 49 sine squared of theta. You can pull out a 49, cosine squared, and then how would I technically make this answer better, best, proper? Absolute values. Absolute values. So should you have an absolute value? Yes. Is there a better answer than the book? Yes. With that, guys, though, I'm pretty sure that's the end. Do you guys see what's going on in section 5.2? No, it's, well, yeah, you would think so, right? But aren't there evens?
They actually credit the even too.
Why would I? Now, this is my updated file. This is what it's going to look like on Monday when we check this homework, because this homework isn't due until Monday. For section 5.2, because it gets kind of tricky and takes some time. Puzzles get hard. Why did I not put any answers for section 5.2 if the problems are going to look like this? Don't you know the answer? Does that make sense? Yeah. Now, does that mean that you might get to this and be like, I don't know if it was legal? But would the book have necessarily have had your exact way of doing it? Maybe not. So I'm not going to, when we grade 5.2 on Monday, I'm not going to give you any even answers. And even the odds that you check in the back might have been gotten a different way. What I'm going to do is open up the whiteboards and be like, hey, which ones didn't we like? And be giving out markers to people who think they have solutions that are legal. And you guys will be not only participating, hopefully by having some of them to help someone else with your version of solving, but hopefully, like, in a sense, grading theirs and being like, wait, is everything legal? Grading with a critical but gracious eye. Ooh, speak the grace and truth. Speak the truth in love. You're going to be testing not only how you did, but also how others did and what would be the best way of getting from a given to approved for you personally. Does that make sense? Okay. But coming back to section 5.1, I don't want to just pop over and be like, oh, so that was easy, right? Are there any odds that we need to go over real quick? Or evens? Yeah. 52. Oh, it's an even. Okay. 52. Is it one we just talked about? I don't think we had 52, Kim. I could peek at it if you want. Yeah, I don't know. I'll still peek at it, though, because if it's hard, Sam. Oh, yeah, I'll go down there. Gavin. 51. Okay. It seems like we don't like the 50s, so Sam, let me freeze the screen here. Let me go take a picture of 51, and then Kim, we'll peek at 52, because it gives the class a good example of something you thought was tricky. And they might see something like it in section 5.2. But first 51, because that was one of the ones that we did have. Actually, I take a picture of both, because you're just trying to find the mistake. Are there things that are illegal that look pretty legal sometimes? Are there things that are wrong that can kind of look right? In life, not just math. You have to have a critical eye. You have to have a critical eye. Even the Bible says, wise as serpents and harmless as doves. Have the wisdom. Have the wisdom. But don't use it wrongly. Sam, are you okay before I get rid of it? Okay. Let's check out 51, 52. 51 is what you had to do. 52, Kim was trying to do too and got confused. 51. Do you guys know why I can kind of understand you didn't like these ones? Why am I highlighting this guy and highlighting these guys? What properties are you thinking that you might need to use? Yeah. Oh, thank you. Oh, sorry. I changed it, but the search must have not changed. I tried to cancel a search and do a new one. Thanks, Adam. Oh, I was so ready for that too. It's okay, we got a life lesson in there at the same time. 51, 52, 51, 52. Oh, use a graphing utility. Then let me ask you guys. First of all, were you in radian mode? Remember, degree mode, the window needs to change drastically. Degree mode, you better just go to your zoom and go zoom trig, because you have to make it go by 90s and 360s, but only going like up one, down one. The zoom, the window has to be super whacked out for degrees. But for radians, it's much more natural. So first of all, you in radians. Second of all, I just want you guys to tell me, what do you see with this guy? What do you see with this guy? Give me a second. I'm actually doing a transformation in my head. Okay. Do you see a bounce-city bounce bounce? Do you? Do you see a bounce-city bounce bounce? Cosine times 1 over tangent time or plus sine? Just put in x's. That's okay. Do you see a bounce-city bounce bounce? I believe that the bounce-city bounce bounce that you should see going up 1, going down 1 would be the one where the bounce-city bounce bounce starts away from the axis. Not on the axis, but away. Why? Well, the one that starts away is cosecant. If you check it out, it starts at 1, starts at -1. And if you look, this is 6.28. If you check out the 0, or like try to do your trace, or if you try to find the maximums and minimums, that's going to be pi over 2 and 3 pi over 2, which is kind of hard. It's going to be a decimal. You'd have to kind of play with that a little bit to see what the decimal is in the unit circle terminology, but or unit circle values. But it sure looks like cosecant. Hey, does that make sense with who this guy is? Isn't that going to be cosine times cosine over sine? Isn't that going to be cosine squared over sine? Wouldn't I need to get a common denominator? Oops. And sometimes sine is sine squared. And what's cosine squared plus sine squared? Now, to be honest, I don't like using my graphing calculator. So I would rather, and I just did that in my head, and I was like, it's cosecant. But anyway, do you guys see the bounce-city bounce bounce? Yeah, Gavin.
So basically, you probably want to do is like put in your calculator.
See if it matched any of the common graphs that we've been dealing with. So, yeah. Yeah. And then you could always do the math and be like, oh, it is cosecant. But they were just trying to give you another variation. This looks so weird, so complicated. Wait, isn't that one of our basics? It's further cementing the idea of some of these trig expressions, like when you put all of this together and maybe in your math, like you're putting formulas together, you're adding formulas together, maybe it could simplify to be something quite basic, and that's why we're working on these skills. Kim, with this, once again, I don't like the calculator. If you had done the exact same idea of looking at a graph, you're seeing if it looks like something basic. I think I might have gotten a common denominator first, actually, to be honest. Not that you had to do the math, Kim, just I didn't want to go to the graphing calculator. This would be 1 over sine times 1 minus cosine squared. If you got a common denominator, that ends up being sine squared. This one, you should have seen something. So even though it was weird and funny, it should have looked like tangent. It should have looked like tangent. Just plug it in your calculator. Follow the directions, kiddos, and say, hey, that looks kind of basic to me. Which basic? Well, identify it. All right. Here we go, section 5.2. Let's go play with puzzles now that we're going to be able to see what they are. Let's go play with puzzles now that we're going to be able to see what they are, what they're supposed to be, where we're supposed to go. You still have a little bit of freedom. to choose your given, to choose your prove. You might totally have to backtrack and be like, I don't like my chosen. I'm going to kind of switch it up. I'm going to go back and try again. My perfectionists who like doing a procedure, following it to get to the right answer, and having it work every time, you're going to get really frustrated at times in this homework. Because you're going to know the answer, and you're going to know whether or not you got it right. It's like a multiple choice question. Like, the right answer isn't there. Sometimes it's going to be like that. Because they're telling you what the right answer is, and you're like, it doesn't match. Either you haven't thought of something, that you could do, or you've already done something wrong, and that could be very frustrating. I'm hoping enough of them are not frustrating to the extent where you can have some fun with the homework on the ones that you get, so that the ones that are frustrating, you're like, it's okay, I'll get through it. She'll give me some hints, she'll give me some tips, she'll give me some tricks, it'll all work out okay. Hopefully this homework won't be a horrible experience. But some of you are like, I like the puzzles that I can get easily, that I can get quickly, that I can get correctly and feel validated by. Others of you are like, no, I like the puzzle process. I like being judged, and I like having to think through all these different options. And I like being faced with a dilemma and trying to figure out how to make it work. You might actually love this section. But those of you that are like, I don't know how to do it, or I don't like it, or it's not working out, and you just give up, might hurt just a little bit. But some of them are easy. Just hear me when I say some of them are hard. Because you could make mistakes in the math. You could make mistakes in the trig. You could make mistakes in the writing of the problem. We've felt that at some point this year, right? But you can't give up. But there are some people, especially in this homework section, and maybe not in the beginning, but by the end, who would have a little whiteboard. Where you guys see how, I guess we haven't really used them in here, but I even have like a page protector with a piece of paper in it, and I have people use these as little baby whiteboards. Just have a tissue, super cheap whiteboard. I had kids by the end of this section that were like, I'm not going to put it on my paper until I've worked it out on a whiteboard first. Why? Why are whiteboards nice? This isn't working. I don't think that was right. Check with Slater. Oh, that was illegal. Whiteboards are nice. So it might be something where either a whiteboard or a scratch piece of paper, you might want to try to make it work first, not on your homework. That's only if like you're super OCD and you like your homework being like the nice, neat, I got it perfectly the first time type of thing, which isn't real life, right? But some people, especially this section, literally went out and bought a whiteboard just to be able to not have to have their homework be messy. Anyway, just an idea. Before we go into some more puzzles, really quickly, I wanted you guys to see the difference between conditional equations and identities. And here's the quick struggle. Because the title of this says verifying identities. Both of these equals. Both of these have an equals, right? Both of them say, hey, the left side equals the right side. They're called two very different types of equations, and they mean two very different things. A conditional equation, which we're going to come back to once we get a lot better at playing with using identities and verifying identities and changing things up. Some conditional equations get pretty sticky, pretty tricky as far as how to get x alone. Because conditional equations, we're trying to get to x equals, and the reason why we're trying to get to x equals is because this is only sometimes true. This is only sometimes true. Cosine can be 0 sometimes, but isn't cosine sometimes a whole lot of other things? Cosine is 0 only sometimes. Now this one, the x is actually inside the sometimes, and cosine is 0 when? Okay, well now 2 times x has to equal those whens. So you have to actually divide by 2. There's a lot of math in this one. Sometimes true. For some angles, for some x's, this is true. What's different over here? Couldn't we do cosine of theta times sine over cosine of theta? Equals, and then couldn't we say, wait a minute, isn't this always true? What's the difference? Besides the fact that you guys know the difference between the word sometimes and the word always, what's going on is over here, for certain x values, for certain thetas, and more specifically, I should say for certain angles, for instance, pi over 4 would be one place where, or one time when that equation is true. This one, only some x's work, but this one, say cosine of pi over 3, tangent of pi over 3, pi over 3. True. I could say cosine of 30 degrees, tangent of 30 degrees, sine of 30 degrees. True. I could say cosine of 17 degrees, tangent of 17 degrees, sine of 17 degrees. True. I could say cosine of negative 5 pi over 12, tangent of negative 5 pi over 12, sine of negative 5 pi over 12. True. This will always be true for any angle that is the same in each and every one. Identities always true, conditional equations sometimes true. So in this section, you're being given identities, and you're going to show, hey, this is always true, no matter what. We're not looking for specific angles. We're not thinking about the unit circle. Sometimes true answers. We're just, oh, hey, guess what? This is always true. So if I ever see this, I can make it that. And if we're going to get to equations where we're trying to find the sometimes true and we see this, oh, it's going to be so complicated. But if we can make it that, oh, it's going to be so much easier. Just to give you a foreshadowing of what's to come. Down here, guidelines for verifying trig identities. I would say, first things first, write a T. First things first, make a T proof. First things first, write a T, make a T proof. You guys have to write the question anyway in your homework, so underneath the question, make a T. Number 1 says, work with how many sides at a time? 1. My way of saying this is choose the given. And in the formatting of the problem, how do you choose a given? You rewrite it. Not only making the T, but you write which one's your given. Underneath the problem, you say, this is my given. So you start there. That's your first step. Just writing the given like you would in geometry. And what's the last step in geometry? Hopefully get to prove, right? But how do we get to the prove? Well, it's going to change every time. It's going to change based on the puzzle. It's going to change based on the problem and the pieces you're going to have to use. But you're trying to get from the given to without the other side, and once you have the prove, you say, hey, look, it matches the prove, and you have a little party and put a check mark and say, done. And hope that if you were to put it on the board, no one could find an error in your proof. Step number 2 is more about clues, not the formatting. Look for opportunities. 2, wait, in homework last night, did it ever ask you to factor? Yes. Did you have to ever add fractions? Wait. What did you have to do to add fractions? Common denominators. Did you ever have to do that? Yep. Square a binomial? Yep, had to do that. 1 plus sine of x squared. You guys had to do that. FOIL. Create a monomial denominator? Huh? Maybe we'll see that one a little bit. Number 3, look for opportunities to use the fundamental identities. Just a quick hint. Number 2 says, let's do some math. Let's do some adding, some subtracting, some multiplying, some dividing, some common denominatoring. Number 2 says, let's do some math. Number 3 says, let's do some plugging in. Plugging in of what? Number 1 is formatting. Number 2 says we can do math to these things. Number 3 says we can plug into these things and plug in what? Identities. We can totally switch it up by saying sine squared is 1 minus cosine squared. We can totally switch it up by making tangent sine over cosine. This one says, note which functions are in the final expression. Look to your proof and see if that tells you which way to go. Number 4, if nothing else works, maybe that's a good thing to take note of. If nothing else works, try to make everything sines and cosines. Make tangent sines over cosines, and secants 1 over cosines, and secant squareds 1 over cosine squareds. If nothing else is working, go back to the beginning and say, fine, I'm making everyone sines and cosines. Legally with the identities, not just randomly putting sines and cosines everywhere. And what does number 5 say? What does number 5 say? I'm going to say don't give up. But what does it say? Always try something. Does fear ever lead us to paralysis or avoidance? Never? You're scared of something, so you put it off till later? You're overwhelmed by something, so you put it off till later? You're frustrated by something, so like I'm just not gonna, whether it's a person, whether it's a situation, whether it's a homework assignment, whether it's a class, I'm just, this is happy, I'll be over here, right? If you get frustrated, what does this say? If it looks scary, what does this say? If you've tried it 5 times in 5 different ways, what does it say? Try something, even a failure can provide insight. Is that a life lesson? Can even a failure make you strong? Teach you something? Yeah, that's a great share of hope, huh? Someone think of a good way of putting that. Even making an attempt that leads to a dead end can provide insight, can help you with where you're supposed to go. God uses that a lot too. A few extra notes. Wait a minute, doesn't this look a lot like homework last night? Let me make it specific to homework last night. I think it was a -4, wasn't it? I think it was a -4. No, because it was -4 plus 1, right?
Sine squared becomes 1 minus.
Oh, you're right. Thank you. So it was plus. If you guys look at this, Robbie, you're totally right. It's a quadratic, but who's the odd man out? So if you see a quadratic, you're going to factor. It's okay. Get a cosine squared in there and do what we did last night. Second one, cannot assume the 2 sides are equal. So you can only work with, don't play with the proof. Well, you can off to the side. You just can't play with it in the actual proof. And the last one says, use techniques from 5.1. Kiddos, your Google Classroom has been updated with this homework. If I were you, I would start playing. We already did one in the back of our homework spirals. Tomorrow, we're going to be like, let's play with the puzzles. Bye, guys. At least right now, it's about playing. Then it's about what the playing teaches.